Hello, class. I think I'm all set to go. I had lunch. It's a beautiful day outside, and here I am. I'm sort of sitting in the darkness in here, but hopefully you can see this okay. And I probably should have a light on it, but unfortunately, well, I could turn these lights on. I don't know if that helps a lot. Might help, might not, because the light, of course, is right above where this is. But that might give it a little better contrast. So what I wanted to do with this lecture is I wanted to take it a step further to the impedance of the inductor and the impedance of the capacitor and how that affects power. We're still talking about power, right? So when we look at the impedance of the inductor, let's just look at that first. We see that the impedance is 0 plus j omega L, right? And of course, that's in ohms. And we also could write that as omega L at an angle of 90 degrees. Positive 90 degrees because we've got a positive here, right? So it's plus. And when we look at, I'm just going to draw the complex plane here again. When we end up looking at that, this is what it is. It's that phasor right there. And of course, the magnitude of that phasor is omega L. And it is at 90 degrees to the positive real axis on my complex plane. So, so we've got that. And so when we then look at how this plays out, right, let's draw our waveform again. And I'm going to start the same way that I did with resistance. I'm going to start with a sine wave. Oh, that's a much better sine wave than I did the last time. So I'm going to start off with a sine wave, and I'm going to say that that is my voltage. I did notice that the colors didn't come through all that well in the last video, so I probably should just do it in black. I do have other colors, maybe the more stark colors, like the blue, seem to come through pretty good, but it also seemed very dark. So we'll see how it works. So I've got my voltage there, and let's say that we've got the same type of circuit that we had last time. This time I'm just going to have an inductor rather than a resistor. And of course, we've still got our positive and negative. I'm still going to say that I'm grounding that, but we always know that really the current is in the voltage. The voltage is a positive one and a negative at the next cycle. You know, you want to think about that too, because this takes into account omega, doesn't it? And we say omega equals 2 pi f, and that's in radians per second. But what's this? And I'm going to actually pick, you know, we're saying that this is, sometimes people can see it better when they have numbers. So let's say that's 10 volts. And let's say that our frequency is going to be 1,000 hertz. Now, 1,000 hertz is not my angular frequency, angular velocity, is it? So 2 pi f, I've got 2 pi, and we know that 2 pi is approximately 6.283, right? 6.283, and of course that is radians per cycle. I'm not going to write that in there because I'm just going to put in my frequency, which is 1,000 hertz, and that gives us 6,000, that's a 6,283 radians per second. I almost could use a thinner Sharpie. I probably should look into that. In fact, I might even be able to use this pen here, but no, I don't think so. I think I need a little more. So let's get back to this. So now we're looking at this, but instead of it being a resistor, it's now an inductor. And we know what the angular frequency is right there, and we know that this is just going to be that times the inductance. So let's say that the inductance at this point is going to be 0.1 Henry. Now we could also say that's 100 millihenries, can't we? So I'll use the 0.1 Henry because that's the primary unit for inductance. And that has all the kilograms and meters and seconds and amps, all the primary units rolled into it and everything else. So we've got that. And so if we look at that then, and we want to find out what the reactance is, omega L, right, which is the reactance, which is 6,283 times 0.1, which would be 628.3 ohms. So if we look at that representation of it up there, omega L at an angle of 90 degrees, which is what we have right here, we can write out what the impedance of the inductor is. It's just going to be 0 plus J 628.3 ohms. We could also write that out in phasor form and say that it is 628.3 ohms at an angle of positive 90 degrees, right? So that's what our impedance is. Now, we know what our voltage is. We know that the voltage, right, is going to be equal to 10 plus J0 volts because we've started it right there. It is our reference. And I could also write the voltage in terms of a phasor, and that would be 10 volts at an angle of 0 degrees. So let's look at what our current looks like now. So our current is going to be equal to voltage divided by impedance, right? Because we know that voltage equals current times impedance. So voltage equals current times impedance. So current has to equal voltage divided by impedance. So if I have 10 volts at an angle of 0 degrees divided by 628.3 ohms at an angle of 90 degrees, what's that going to give me? Well, 10 volts divided by 628.3 ohms equals 0.0159 amps, right? And those would be peak amps. And then what would our angle be? We've got 0 in the numerator and 90 in the denominator, so it's 0 minus 90, so it would be minus 90 degrees. So 0.0159 amps. That's the peak voltage, remember. So I could also say that this would be 15.9 milliamps, and again, still the same angle, minus 90 degrees. So that gives us I. And what is that minus 90 degrees? How would I draw the current in regard to the voltage? Well, let's look at that now. The current is actually 15.9 milliamps at minus 90 degrees. If I had to write that out, I of t, right? I of t would be equal to 15.9 milliamps times the sine of omega t minus 90 degrees. That's right. That's how the phasor form translates into this form, right? Sine of omega t minus 90 degrees. Now, if you remember before, I said if it's a positive, it shifts the curve to the left. But when it's a negative, it shifts the curve to the right. And so if I were to shift the curve to the right, let's take this curve right here, and then we're going to shift it to the right. We're going to shift it to the right how far? 90 degrees. So minus 90 degrees, well, this would be my 90-degree mark, wouldn't it? Right? Isn't that 1/4 of that wave? So that's my 90-degree mark. So if I were to shift this wave by 90 degrees, then the wave would look like this. Does everyone see that? I don't know if you can see the blue so well. It also has a much thicker brush, but the V is the black one that starts right from 0 and goes this way, and then the current is shifted by 90 degrees. And which way is it shifted? To the right. Negative shifts to the right. I know I've said this before, but it's, you know, you want to really get this point. Positive shifts to the left. Make sure you put that in your thing. So you can see now that if I was to continue this on, and this would be what the current is, the current would actually be shifted to the right. Now you might say, well, why is that minus? Why does that show that it's a minus? And what's leading and what's lagging? Now, in this, what you can see is that the voltage leads the current, right? Now you're probably saying, no, I don't. The voltage leads the current. The voltage is to the left of the current, and that's what I want to point out. That's something that usually is not really understood well by students. Let's look at the line that we have here. Don't even worry about the amplitude. Let's look at the line that I have. Now, what is that? That's time, isn't it? Now, let's go back and let's say that right here is 1900. Right there, right at the beginning is 1900. And then let's say that right here, if I just follow that 90 degrees down, well, that's 1950, right? And that would be right, wouldn't it? Because isn't time going in this direction? So this would be 1900 and this would be 1950. Well, what happened first? 1900 or 1950? Does everyone see that? Does everyone see that the current is lagging? And that's because it's coming later. The first thing that happens is the voltage waveform. The voltage waveform starts here in 1900, let's say, and then starts going up. In fact, the current waveform doesn't even start until this one is already up to 1950. So you can see it's later in time. That's what I'm really trying to point out, is that this one happened first. Happened first. And then this happened second, right? So it's in there second. So the voltage is leading the current. Voltage leads, and that means to the left, current. You could say that the current lags behind the voltage, that the voltage starts up like this, and then the current, when it gets to a maximum, then the current starts up, right? So this one starts first, this one starts second, when this one has already gone through 90 degrees of its phase. So that is everything that you ever wanted to know about that. I'm sorry, it's not everything you wanted to know about that, but because what are we doing here? It's power, isn't it? So let's look at the power for that waveform. So you can see the power in this regard, and you could look at this too over here, and you could say, okay, well, how do I actually work the power out for this inductor? Because it's going to be VI. So the power, of course, is in RMS. So if I'm talking about V, I'm talking about 7.071 volts RMS, right, at an angle of 0 degrees. And then I, which I've got over here, is 15.9 milliamps, but of course that's milliamps peak, isn't it? There's always peak here. So we've got to multiply that 15.9 by 0.7071. 15.9 times 0.7071 equals 11.24. So I've got 11.24 milliamps RMS. Remember, I'm using milli here, so I have to always put in times 10 to the minus 3. And then that angle that's coming in at is minus 90 degrees, right? So if I multiply those all out, I end up getting 79.5. Power equals 79.5 milliwatts at an angle of minus 90 degrees. Why is it minus 90? Because I've got 0 plus a minus 90, and so that gives me minus 90 degrees. Now, I also want to point out another thing, too. Now, I've sort of continued this on because I wanted to show that this is negative. So I've got negative current there, but I've got positive voltage. So what is the power in this first quarter wave that I've got here? Minus and plus. Those would give me a minus power, wouldn't they? I'll try to use the red. I don't know if the red will come through that well, but let's try it. So in the first one, I get a minus power. Let's say that. Now, how about the second one when I go from here to here? Now, you can see that that's becoming positive, and the voltage is still positive, so I get a positive power. So these are the power things right there. They may come out black. I don't know. They look bright red to me, and I'm hoping that the camera's picking it up, but we'll see. So that's the power. That's the power back. Now, in the next one, what's the next? So I've got a positive here and a negative here. So that gives me a negative power pulse right there. And for the last one, you can see that this is minus and this is minus at the same time. So it looks like this. I want you to look at two things with the power curve. First of all, the power curve is twice the frequency of the regular voltage or current. So power wave is 2 times the frequency of voltage or current frequency, right? You can see that because this is going up. There's one in the first half wavelength of the voltage. You've already got a full cycle of the power, right? And so you can also see this. What's really happening here going through the I've got power that is fluxing in one direction, and then it's fluxing in the other direction. Then it's fluxing in the direction again, then it's fluxing in the other direction. Now, that's going through an inductor. And that means that the current through that inductor is changing direction too. You can see that the current here is negative, then the current becomes positive, then the current is still positive, but the voltage has become negative. And so then the voltage is coming back the other way. But as far as power flow goes, I've got power flowing in, power flowing out. So I've got something that's heating up the inductor, and I've got something that's cooling down the inductor, if you want to think of it in terms of heat. Actually, you can't really think in terms of that because these are ideal components, and so there is no resistance. It would be like a superconductor inductor. The truth is that all inductors, because they're round with regular wire, have resistance associated with them. Anyway, I just wanted to show you how the power flows there. Now, we're going to see that same thing for a capacitor, and I'm going to stop the video here and put this up and then do the next video. If I can even find out where the little arrow is down here. Where are you, Mr. Arrow? There you are. Okay, and I'll put the next video up.